Let's go to another instrument called the meter bridge and have a look at one of its use. And meter bridge is based on something called Wheatstone bridge. You would have, I think, heard about this instrument. Meter bridge is based on Wheatstone bridge. It's a very simple instrument, people, very simple instrument. As the name says, it has got a wire of 1 meter length. So this is the wire of 1 meter length, and maybe this wire is called AB or something. So there is a wire AB of 1 meter length, and you can read along a scale that is kept along AB the distances along AB, right? So there is a scale kept along AB, and if you read on that scale, you will get the distances along AB. And attached to the same circuit in parallel are a resistance box. So you've got somewhere a resistance box which can be used to insert a very accurate value of resistance. So you've got a resistance box, and somewhere you have got a space to fit in some kind of unknown resistor. Unknown resistor. Let's call it X. Let's not call it X like this. Let us draw the resistor and call it X. Right. And what you do is you join the circuit, and this wire AB is made up of the same nichrome thing out of which we made the potentiometer wire, because we want this wire AB to have significant amount of resistance. And then we attach a cell in the circuit, something like this, and you have got a Wheatstone bridge kind of apparatus. And what you do is, from the upper branch to the lower branch, you create a contact, a sliding contact with the help of a jockey and with a galvanometer in between. So you've got a galvanometer somewhere, G, and you've got a jockey. And what you will do is, you will keep a fixed value of resistance in the resistance box, right? So you are going to get a fixed value of R from there, and R is to X will then be a certain ratio. It will be some ratio. We don't know what ratio because X is still unknown. And then you will try to find out the null point on this wire AB with the help of the jockey. And wherever you find the null point, there you will say that if I find out the resistance of the resistance box on the left hand side of the wire, their ratio should be the same as the ratio of X to the resistance of the right side of the wire. As easy as that. So maybe I have the null point somewhere here at C, right? So let me take this jockey and put it in contact at some place C, and let me say that the null point is at C. So if null point is at C, then null point is at C, then resistance box divided by resistance of AC is equal to X divided by resistance of CB. And we can easily find the resistances of AC and CB, because we know that for this meter bridge wire, for wire AB, in fact not AB, I can do AC in one go. So for wire AC, I can say resistance of AC will be rho LAC divided by area of cross section, and similarly for wire CB, I can say resistance of CB is equal to rho of this wire times length CB by A, right? And so I can insert these two guys in this upper equation here, and what I will get is, what I will end up having is, therefore resistance box divided by rho length by area is equal to X divided by rho length by area. And I can throw away rho and area, provided the wire is homogeneous and the area of cross section is the same everywhere, but those are the conditions that will anyways be met. So resistance box value divided by length AC, which I will start calling L1 or something. So L1 is equal to X divided by L2, right? And we don't have to take two separate measurements. The reason we are saying that this is a meter bridge is because this wire AB is 1 meter long. So if you know the initial length L1, the remaining length automatically becomes 100 minus L1. So this is L1 and the remaining length from C to B is 100 minus L1. So this equation finally becomes a resistance box value divided by L1 is equal to X by 100 minus L1. Done. And this is the final equation that you should use. So with one measurement, you will be able to figure out the value of X. Now there are a few important things that you should know about the meter bridge. One of them being that it is most sensitive if you try to find out the null point at the center. So suppose you do an experiment and you don't get the null point near the center. You get the null point maybe very close to A. That means the value that you have chosen in the resistance box is very small. And that is why you have got this point C very close to A, so that the resistance of this portion AC is very small. So what you do is, you don't go for that value, you change the resistance in the resistance box, you make it larger so that the null point shifts closer to the center of the wire. And if you get the null point somewhere in the center, maybe say from the 35 centimeter mark to maybe around the 65 centimeter mark, that's fine. That's the region in which the equipment is most sensitive. There is a reason for that, but we are not going to go into that also. You don't need it. But they don't usually give such easy questions in meter bridge. So the question that they give you is, what you may have in the examination is something of this kind. You will have a meter bridge and you are doing an experiment with the meter bridge. So you have arranged for a resistance box. Let me just call it RB. And you have got two unknown resistors, right? They are attached in series once. So you have got P and you have got Q, and you have attached the meter bridge wire. Okay, let me put it like this. The orange colored wire is here. This is the meter bridge wire. And then what you do is you have put the other things in place, not an issue. The wire, you are calling it AB, so this is AB wire, and you take the jockey out of the center point with the help of a galvanometer or something, and you find the null point. Now when you find the null point, you are not going to get P or Q, you are going to get P plus Q, right? So you do this experiment once and you arrange PQ in series like this, and you find that the null point is at a distance L1 from A. And you do the same experiment again and you put PQ in parallel, right? So in the second case, what you will do is you will put P and Q in parallel like this, P and maybe you have Q, and you have got two equations now, because in the first case the null point is L1 away from A, in the second case the null point is L2 away from A. Null point is L1 away from A, and in the second case null point is L2 away from A. And so you can say that resistance box by L1 is going to be P plus Q by 100 minus L1, and you can say in the second case resistance box by L2 is going to be PQ by P plus Q divided by 100 minus L2, where you should keep in mind that the values RB, L1 are known, and in the right hand side equation RB and L2 are known. So you will get something like, if you just rearrange this equation, you will get something like P plus Q is equal to alpha, and on the other side you will get PQ by P plus Q is equal to beta, where alpha is equal to resistance box value times 100 minus L1 divided by L1, and on the other side where beta is equal to resistance box value multiplied by 100 minus L2 divided by L2. Right, so we have got these values, and alpha and beta will be known numbers. So what you can do on the right hand side here is you will have PQ is equal to alpha into beta, because P plus Q is alpha. Now you know P plus Q and you know PQ, and you have to find out P and Q. So the standard trick to doing this is, using algebra again, and you will say P minus Q whole square is equal to P plus Q whole square minus 4PQ. Those who doubt it can expand and see. And you will have alpha square minus 4 alpha beta. So therefore P minus Q becomes alpha square minus 4 alpha beta within a square root. And now you have got two equations. Let me call this P plus Q equation as 1, and let me call this P minus Q equation as 2. So you add 1 and 2, Q will go off and you will be able to find out P. So therefore P is equal to alpha plus root of alpha square minus 4 alpha beta divided by 2, and you will be able to figure out the value of Q if you subtract 2 from 1. So P goes off and Q will be alpha minus root of alpha square minus 4 alpha beta divided by 2. Done.